All right, so hello, welcome to our fall semester training series dedicated to the use of our flagship AI system called HAL. We are starting this series first with an introduction to how to get started on HAL, and this will follow up by tutorials on introduction to machine learning with neural networks and tutorials on introduction to PyTorch and TensorFlow, and we'll continue from there. So my name is Volodymyr Kindratenko. I am the director for the Center for AI Innovation. The machine that I will be talking about is funded by the National Science Foundation and has been in operations for some number of years already. And we have quite a large number of users, and this is always a starting point for them to actually look at this training materials as a way to understand how the system is built, how it's functioning, and how to make the best use of it. So with that, today's tutorial is about the whole system in general and about the ways we envision users are to be using it. The URL that is posted on this first slide basically is the URL to the wiki page that contains all the documentation about the system, all the application forms, how to get an account on the system, to all the documentation materials which explain how to use different components of the system. So make sure you take a note of this and you use this wiki page with all the reference materials. So the machine, the whole system, is an SF-funded IBM cluster, which was developed here at NCSA to provide the deep learning community on campus with the compute capability necessary to train machine learning models at scale. In order to build this machine, we surveyed the user community at that time, and we asked the question, what's missing on campus? And one of the answers was that there is no centralized big enough resource, not even centralized, but big enough resource to train models, non-trivially sized models with sufficient performance. And so we built this machine in response to that. So the system consists of 16 compute nodes. These are IBM Power 9 nodes, each of which is outfitted with some number of GPUs, or 64 GPUs altogether, and served by an all-flash storage, over 300 terabytes of usable space that is served over high-speed network. So the storage system is sort of well-balanced to supply all 64 GPUs with data to train models. And the name for this machine is HAL, which in our terminology states for Hardware Accelerated Learning Cluster, but we obviously named it after the AI that was portrayed in the Space Odyssey, 2001 the Space Odyssey movie, and then the book that this movie is based on. And in that story, there was an AI on the spaceship. That AI actually was invented and built at the Urbana campus of University of Illinois. So we obviously wanted to name our system that way. So here is the description, or the diagram that describes how the system looks like. So two racks of equipment. One rack is loaded with compute nodes, and there are a couple of switches, infinite-bit switches there, and the other rack has all the other elements in it. So it has, in particular, it has the storage, it has the login node, it has the data node, it has some auxiliary nodes which are used for different purposes. And as of recently, it also has DGX A100 systems that is also essentially part of the available hardware, but it's not actually integrated with the rest of the cluster. Nevertheless, it's available for users to use. So as I mentioned, the system consists of 16 compute nodes. These are IBM AC922 nodes. If anybody is interested in technical characteristics, and they are here, each node has 2 CPU sockets, 20 core CPUs, has 256 gigabytes of DDR4 memory. And what's important for us is 4 NVIDIA V100 GPUs. These are GPUs interconnected through NVLink, and this NVLink goes all the way to the CPU. And so all in all, this interconnect is what makes this machine to stand out, as it provides sufficient bandwidth to enable very fast communication between the GPUs within the node and also across the nodes through the InfiniBand. There are two EDR IB switches. They operate at 100 gigabits per link. Each compute node has two adapters, and these adapters, one of them is used to provide storage connectivity to the storage system, and the other one is used to provide connectivity between the nodes. So any training jobs can sort of take advantage of having fast access to data and also fast, low latency interconnect to other nodes. There is a login node somewhere there. There is a data transfer node. There is an interface node for the Open OnDemand web interface, and which provides all kinds of services. And I will talk about that a bit later. And then there is also the flash array. We are using DDN all-flash storage array that exposes something of the order of 360 terabytes of usable storage, and provide having the spectrum scale file system running on top of it. So this is a parallel file system that is cross-mounted across all of the compute nodes that can make use of it. On the software side, the cluster is using Red Hat Enterprise 8.4 operating system. We started with CentOS and eventually upgraded to Red Hat. It has the latest CUDA software stack and all the IBM compilers, and it also has this what is the sort of the tool set that provides all these machine learning tools is the OpenCAII, Open Compute Environment collection of tools which are optimized for this architecture. Those include PyTorch, TensorFlow, the latest versions, or pretty current versions at least, as well as all the other tools necessary for them. This cluster is managed by a Slurm scheduler. This scheduler enables users to submit jobs. These jobs will be allocated to resources, will be executed on those resources, and the results will be returned to the users. And I will talk about this a bit later. So, this is the basic building block of the system is IBM AC 922 server. And so what's important to mention here that there are two CPUs, two IBM Power 9 CPUs, the 20 core each. Each core is set up to run 4 compute threads. So basically, each of these processors is able to run 80 threads and 160 between two of them. They have a high-speed memory interconnect to the CPU. When we built this system, this was perhaps one of the highest-speed interconnects to between the CPU and memory. And there is also a high-speed interconnect to the GPUs, where a pair of GPUs is connected per processor, and this interconnect is done with the help of NVIDIA NVMe Link interconnect. And so this configuration enables very high-speed data exchange between the GPUs in the system, and which is really important both for feeding data from memory into the NVIDIA GPUs and also for exchanging data between the GPUs, particularly for multi-GPU model training applications. Just to give some more details about the Power 9 CPU, as I mentioned it, 20 cores with SMT4 capability, so meaning 4 threads per core. There is some decent amount of cache. And what's most important is the NVLink 2.0 interconnect and support for PCIe Gen 4. So this PCIe Gen 4 interconnect is used by IB, by the InfiniBand interface cards. And then NVLink, as I mentioned, it is used to connect to the GPUs and provide connectivity between the GPUs as well. This is one of the very few architectures in which GPUs are connected directly to the CPUs through NVLink. Typically, such an interconnect doesn't exist. Only GPU to GPU connection is done using NVLink, and in this generation of hardware, IBM provided that interconnect all the way down to the CPU. Now, from the point of view of machine learning, sort of the main workhorse here is, of course, the GPUs. So we have 4 GPUs per node, is 16 nodes, that gives us 64 GPUs altogether. These are NVIDIA V100 GPUs. This machine was built when these GPUs only became available, and so at that point it was state-of-the-art deployment. So by today's measures, this is previous generation of GPUs, but they still continue to be very capable hardware for running machine learning applications. Each of these GPUs is capable of providing up to 15 teraflops in single precision computations, and even more than that in integer computations or reduced precision computations, 16-bit floating point computations. They have AI-enabled tensor cores, which are very well suited for running computations on tensors as sort of the basic building block for machine learning applications. So the GPUs come with 16 gigabytes of HBMI2 memory that runs at 900 gigabytes per second bandwidth to supply data to the GPUs. And so this is actually what made the GPUs to be very popular for deep learning applications. There is some amount of caches and all that, but the main thing here is that the compute power, the GPUs were basically, this was the first generation GPUs which were specifically built with machine learning applications in mind and provided these additional capabilities for that purpose. And combined it with the high memory bandwidth, they were ideal for the machine learning training jobs. So on the software stack, as I already mentioned it, we have Red Hat Enterprise Linux, and with the collection of compilers which corresponds to that distribution and also to the latest versions provided by NVIDIA. We continuously update these tools. We have periodic maintenance every quarter or so, where we look at the available software libraries and all the tools, and we periodically update those on the system. So we will continue to do that in the near future, or in the foreseen future, to ensure that we have the latest software stack. And we also update the OpenCAII environment. Actually, so I haven't updated the slide, but our current version of OpenCAII is 1.6.1. This is one of the latest versions of OpenCAII, compiled with all the with PyTorch and TensorFlow, with support for GPUs that are tuned for this particular application. And we have all the other components necessary to make good use of the system. We do support containers through Singularity platform, and it is possible to put your job into a Singularity container and submit it this way. So on the sort of user interaction side, so we have two login nodes. We typically have one of these login nodes enabled at a time, and the other one is available as a backup. So these are also IBM Power 9 servers. They don't have GPUs, but they have the same architecture. They basically have the same chips, or nearly identical chips to what's in the compute nodes. So they run the same operating system, and they provide sort of consistent environment throughout the entire setup. So users connect to one of these nodes through secure shell, and or through the SFTP if they need to transfer data. We do have a data transfer node, which also runs Globus endpoint. So if users have a lot of data that needs to be translated or transferred into the systems, then that Globus endpoint can be used for this purpose. And there are instructions on the wiki page describing how to use a Globus endpoint for this. The environment management is done on the systems through modules. So LMOD, which is Lua-based modular system for dynamically altering environments. We have all of these packages which are installed on the system. So compilers, the OpenCAII modules, all kinds of additional tools that are installed in the systems. They all are available through the LMOD, and they can be loaded as a module. So you can build your own environment essentially from those modules. And we also have Anaconda as a main sort of distribution for Python packages, and we provide some baseline environments which can be cloned, and then you can add into those environments your own components that are missing from some of the sort of main environments. This LMOD, basically the user interface to it through the module command that you execute from the command line interface. And you can enumerate which modules are available in the system, which modules are loaded in your environment, and which modules you want to load or unload. So so that's that. And so, you know, there is documentation about this, and there is a list of specific modules and specific versions of those modules which are available. So if you need to bring up a particular environment, you should consult with the documentation to see what it is that you need. On the workload management, we use Slurm. We use Slurm to put jobs into the queue. And so these jobs from the queue will be assigned to a particular hardware for execution. And this workload manager enables us to, on one side, ensure that everybody gets a fair share use of resources, and on the other side, make sure that those resources are efficiently utilized by all the users. Part of this presentation will be about how to properly use the Slurm workload manager to ensure that your job gets executed with the resources that you really need, while also allowing other users to continue to run their programs. So one of the the main basic, the main most important computational resource in this system, of course, is GPU. So with 64 GPUs, we can have up to 64 unique jobs running, each utilizing a single GPU. Of course, if users require, if their applications are capable of using more than one GPU, then the number of users will be reduced by that. But generally speaking, we majority of the users are just using one GPU at a time, so they can altogether we can have up to 64 GPUs. So these are sort of the basic policy assumptions that we made. These assumptions are needed to ensure that basically everybody has a fair chance to get his computations carried out, and that the system is not bogged down by a single user who is taking all the resources or taking over the entire system. So thus a user cannot have more than 5 running jobs at a time, cannot have more than 5 active nodes per user, no more than 16 active GPUs per user, and the maximum job duration is 24 hours. Now, saying that, of course, you can imagine that sometimes you need more resources, and sometimes you also need longer running jobs and all that. We can accommodate all of those requirements by special reservations. So if you have a paper due deadline coming up and you urgently need something to be computed, we can always create a reservation which will override some of these rules. So you can get more GPUs, or you can, in particular, you can get more time, more than 24 hours per job. So if you have some requirements that do not fall into this usage policies, then email us and we will be happy to work with you to accommodate your requirements. Now, talking about using the Slurm. So typically, when you run something through Slurm, you need to specify all kinds of parameters. You need to tell. So Slurm has a very sort of great level of fine granularity to what you can describe about your environment. You can specify how many compute nodes you need, how many CPUs you need there, how many CPU cores, how many threads per those cores, how much memory per CPU, and of course, if you are using GPUs, how many GPUs to use, and the amount of time. And so by the time you have to specify all these parameters, your command line argument becomes very, very long. So what's shown here is an example of requesting a compute node, complete compute node with 4 GPUs and all the CPU cores for the period of 24 hours to run an interactive job. So that's a long line of instructions to type in, and that's a line of instructions where it's very easy to come up with configurations that cannot be satisfied, that cannot be provided. And also you can easily make a typo somewhere here. So what we really look at that is what would be a typical use case for this, and we realize that if somebody needs just one GPU to train train his model, then typically he will not request more than some limited number of CPU cores. There is no need to request the entire node for that. Typically, maybe 16 or 20 cores will be sufficient for this purpose. And also probably not the whole memory is needed. and so on. And so looking at these requirements, we came up with this sort of a wrapper that enables us to streamline the process of requesting resources on the system. We developed this wrapper that enables you to type in a much shorter line, command line, and it will give you a well-balanced computational unit that will have a GPU, will have some number of CPU cores associated with it, have some amount of memory, and so on. Of course, you can always override. You can take that command line and kind of rewrite it in your own way if you feel that you need more. But for vast majority of use cases, this default configurations that we developed is sufficient. And so we developed this wrapper that has, so typically in this Slurm commands, you will have srun or sq or sin for commands. We developed the wrapper which has s and then followed by w. So Slurm wrapper run and Slurm wrapper sq and so on. And these types of, and so this wrapper figures out all the configuration parameters for you based on very minimal input from you. So it requires at most 4 options, and some of them are actually optional. The only option which is really required is partition. That is, how many GPUs do you need? Do you need 1 GPU, 2 or 3 or 4 GPUs, or CPUs? And so you can just specify the partition, CPU or GPU partition. You can fine-tune how many CPU cores per GPU are needed, but if you don't provide that flag, then there will be some default value. You can fine-tune how much time you need, but if not, then you will be given some default amount of time. And also, if you want to use a singularity container, so that will build and launch a container for you. And if you just run this command with just the GPU, we just asking for GPU partition, say GPU X1, this is the name of the partition, then you will automatically get 16 CPU cores, almost 20 gigabytes of memory, 1 GPU, and for 4 hours of time. And for interactive use. And so in many cases, this configuration is what's sufficient. You get this machine for 4 hours to try something. Typically you will, if this is an interactive job, you probably most likely will be, testing something. So you sooner or later figure out how to run it correctly, and then you can submit a batch job. But it's a short amount of time, so you're not going to take over the entire system for a long period of time. So, some additional sort of notes about this. Typically, when you submit a job with sort of minimal requirements, it ends up in the debug queue. This debug queue enables you to run anywhere between 1 to 4 GPUs and CPUs, and for some short period of time. So that's debug queue is kind of high availability queue. We always try to put computations into that queue first if they meet this requirement, that this is just a single node job. To run the singularity, we have to supply this -s flag with the name of singularity container. So there is a collection of containers which are already pre-built. If you need a new container, we can work with you to build a new container, and we can always add your containers to the pool of available containers in our registry. And so, for example, in this example, we are using a container called Power AI, which has all the tools that came with IBM Power AI package. And thus, with this wrapper, basically, this very long Slurm command becomes just this: swrun go to use of 4 GPUs. That was what used to correspond to this GRS flag here. GPU X4 will request all 4 GPUs. If you want to use all CPU cores, and all, then the -C40 will tell us how many cores to use, and that corresponds to all these other flags which say how many cores for how many threads per cores and so on, and for the amount of time, which is T24 means 24 hours. So this shorter command will result in executing exactly the same code or generating exactly the same command to Slurm. So that greatly simplifies it. There is also, this srun enables you to run, for example, interactive jobs. If you want to submit something to a batch, we have a wrapper which overrides the as-batch command. This wrapper also requires just a few parameters, most of which will be inferred by the system based on just the partition requirements, but you do have an ability to override those parameters. Again, so partitions could be GPUs or CPUs, and other parameters as needed. So here's an example of the SW batch example script. So the script is going to execute this mnist train Python script on some number of compute nodes, and so this as batch commands will be basically used to specify the configuration of the node. So for example, this dash partition command says that we want to use the GPU for 4 hours, 1 node, that many tasks per node, that many cores per socket, and so on. So much memory and just 1 GPU. So that's actually the conventional batch Slurm batch script. In our wrapper script, you only have to specify this one line, one parameter. Just specify the partition GPU x1, and all these other parameters will be inferred to be this values based on that partition. Now, of course, if you say everything is good except I need more time, so instead of 4 hours I need 24 hours, for example, then you can actually just add one more parameter that is missing, and that will override this default parameter. But you don't need to add anything else if the default values are sufficient. And so instead of running as batch with some script, you can just run as w batch with some script. So that's that. So this documentation is on the wiki, and this is sort of an easy way to learn how to submit jobs to the system by using the wrapper, Slurm wrapper, instead of using the wrapper with the Slurm directly, which is much more complex. So to provide some feedback to the users and to provide some sort of enhanced user interface, we also have SWQ command. So this command essentially provides this graphical output inside of your terminal, shell terminal. So you may need to enlarge your terminal so that all this fits into one line, but nevertheless, all you need is just a terminal. So typically, if you want to see what's happening on the system in terms of what jobs are running and all that, you will use sq command, and then sq command is going to tell you what jobs are running, what's their status, if they are pending or if they are running, or if they failed it, then for what reasons they failed it, and so on. So you can get more detailed information from sq. However, if you only want to see what's going on the system, how nodes are used, and if there are any free nodes, you can use SWQ, and you will get this feedback. This feedback basically tells for a given node, so there is a list of all 16 nodes here, you have a visual feedback which tells how many CPU cores are requested and in use, actually are requested by the jobs. So on this node, there looks like 64 CPU cores are requested. On some other nodes, looks like there is, 100-something nodes are requested. There are some nodes which they don't have anything running on them. It also tells you who are the users who are running the jobs on the system. And so, there are some that, for example, this node 16 has several users. Their jobs are running across multiple CPU cores here. And also tells the job IDs, so you can see what their job IDs, and in particular, this matters if you know what your job ID is, and you can see where it is located. And then it also tells which GPUs are occupied. So, for example, looks like pretty much so everywhere there is a blue color on this text, GPU text. It means that this GPU is requested by the job, and if this GPU text is not highlighted here, then it means it's free, it's available. So this visual interface helps you to sort of get a very quick glance of what's happening with the system, how is it used or not. So there are some rules and there are some guidance about how to properly use this Slurm wrapper. In particular, we have this list of frequently asked questions on our wiki that answer some of the questions about how to configure your Slurm submission. So typically you can always find more information by just running ask you and seeing what the status of your job is. You can actually run sinfo to see what the status of the overall cluster is. So there is, there is more. There are more commands out there that you can use to find more details about the status of your job. There are some typical or common mistakes that in using it that we outline in our frequently asked questions. Okay, of course, this mode of use requires users to be relatively proficient with working through the command line interface, through the terminal. So it means that you have SSH into the head node. You have to write your job files using your favorite text editor, such as VI, because this is a command line interface, or maybe Nano. You then have to issue these commands through the command line interface and so on. And actually what we realize is that there is a very large pool of users of the system who do not necessarily want to work with a command line interface. They used to work with Jupyter Notebook on their computers, their laptops. They would like to have a similar environment to go forward. So they don't want to spend time on figuring out how to use VI text editor and so on. And so for those users, and this is actually a very popular tool, we provide a web-based interface called Open OnDemand. So Open OnDemand is the interface that developed at one of the supercomputing centers to basically provide a front end, web-based front end to Slurm. And this Open OnDemand interface enables to just use your web browser to interact with the system, and basically derives the same functionality through the web browser as you would derive through the command line interface. It enables you to manage files, so you can create files, copy files, upload files, download files. It enables you to submit and monitor jobs through this web interface. It also provides you shell access if needed. So you can always get the command line interface through inside your web browser, which means that you don't need to have a SSH client on your laptop anymore. You can just, all you need is really just a web browser. And it also provides you very convenient access to tools such as Jupyter Notebook, TensorBoard, VS Code, which also runs in the web browser. And so you don't need to have that VS Code deployed on your computer, and you don't need to remotely connect to the server. You basically have it all in one package. And H2O AI applications, and there are some other applications that we have recently deployed. So to get started with this, there is a web page, and this link to that web URL that leads to this Open OnDemand interface posted on the wiki. So you just follow that link, and when you get to it, you have to log into this interface using NCSA Credentials Manager login screen. This also, so you need to have a NCSA username, but you also have to have an account on the system. So when you request an account and it gets approved, only then you will be able to log in into this server. Once you log in, you need also to have a dual factor authentication established somewhere. The recommendation is to have it in your cell phone through the Duo app. After you provide username and password, you will see the screen where a Duo request will be sent to your mobile device. You have to confirm it. Once it's confirmed, you will end up on this page. It looks like that, which basically says, welcome to this cluster, and provides you with some interface through this drop-down menus that enable you to invoke different services. So from there, you can go to the files page, which enables you to have access to the files in your home directory. Basically, so the file system is cross-mounted across all of the compute nodes, as well as the login node and the Open OnDemand node, the node that runs this interface. So you see access to exactly the same files within exactly the same range of permissions that you have on all of the compute nodes. So this is exactly the same permissions as on all the compute nodes. And you can manipulate with those files or work with those files through this interface within the permissions given to you. So if this file's in your home directory, then you could do whatever you want with them. If this file's in somebody else's directory, you don't have access to them. So another panel is here is the panel that enables you to, first of all, monitor for the jobs that are running on the system. So you can, by default, you only see jobs which belong to you, but you can also ask to show all of the jobs, and you will be able to see all of the jobs running on the system. And you can also get a bit of information about the jobs, like what kind of resources they requested, and how long have they been running, for how long they have been allocated for, and so on. This is read-only information, so you can get an idea about the status of the cluster, but that's about it. You will not be able to change anything here. There is a job composer which enables you to use web-based interface to launch a job. So you can specify which script to launch. You can specify some of the job parameters. And this composer is going to eventually provide the command to the Slurm backend to launch your job according to the scripts that you provide, or according to the specifications that you provide. And so this way you can easily launch job without actually the need to go into the web interface. So you can use file interface to edit files and type in whatever the commands you need to have in those files to run your jobs. And then you can use this job composer panel to use those scripts that you type it in, or those files that you type it in to launch the actual jobs. So this eliminates the need for command line interface completely if you are if you're not doing anything too specialized, and if everything can be accomplished through this panel. As I mentioned, of course, there is command line interface as well. So if you request that interface, you will be brought to a login page, which will basically redirect you and will enable you to log in into the head node, from there you can have a command line interface, like as if you were just using the remote shell to connect to the terminal, except that to connect to the server, except that it's only within the web browser. This still requires a dual authentication, so just like with SSH into the system, for the you always have to use secondary authentication. Okay, of course, the most important tools and the most interesting tools that users are using these days, of course, are the ones that sort of provide sort of a more higher level functionality, such as Jupyter Notebook interface. So there is a set of interactive applications, including Jupyter Notebook. So when you click on this panel, you will be asked to provide some configuration parameters, what resources are needed to run your Jupyter Notebook. So again, you can say, I need 1 or 2 or more GPUs. You also have the ability to specify how many CPU cores you need. And if you have a reservation, then there is a field to specify this reservation. Then when you click on the launch button, this will put the job of running Jupyter Notebook into the queue. And if there is an available resource, or when there is available resource, this job will be executed. And you will get back a page that will have a link saying that Jupyter Notebook server is running for you on some compute node, whichever node happened to be available to run. Click on this link and you will get your Jupyter Notebook. And that Jupyter Notebook is just a Jupyter Notebook within your web browser as your usual Jupyter Notebook. You can open Jupyter notebooks and work with them as you usually do. There you need to choose a kernel. We provide a whole collection of kernels. This enables you to bring in a particular environment right away with a particular set of tools. So these kernels, there is a set of kernels which are already precompiled that have all the necessary tools for specific tasks. So you have to make a selection which kernel you want to use for this purpose. In addition to Jupyter Notebook, we also have a Jupyter Lab. This is again another application that you can schedule Just like with Jupyter Notebook, you have to provide something about what resources you need to execute it, and then you will be directed to a page where eventually you will see a button saying you can click on this button to open Jupyter Lab. And so here is a Jupyter Lab with all the all the notebooks that are available in your directory or something like that. So you basically have the full functionality of Jupyter Lab in your browser. This Jupyter Lab is running on one of the compute nodes within with the resources that you requested. So if you ask it 2 GPUs, you will see 2 GPUs that are available for you, and with all the functionality. So you can also open terminal. You can run all these notebooks and do what you typically would do with Jupyter Lab. Another interactive application that we have is H2O Flow. This application essentially has a collection of machine learning tools which can be used without programming. So these tools enable you to, through the web interface, specify your input data, specify if you need to use just a subset of that input data, specify what sort of processes to run on that input data, how to pre-process it, maybe how to normalize it or filter, specify what machine learning model to run, and there is a whole collection of those running, from simple ones, from clustering to some neural networks, and eventually you can basically, by just clicking mouse here and there, you can sort of configure the entire flow of the computation, including how you want to see the results. So this is sort of zero programming approach to applying complex machine learning models through the web-based interface. Now, there is some decent amount of work that one has to do to be able to use this tool, because you have to specify, how your data looks like, what to do with this data. You have to specify a lot of model parameters that, some of them are not as obvious as they might sound. So you have a lot of choices there to make. But there is also an AutoML option there, where this tool is going to try to pull in several models and run analysis with your data on using different models, and then you can sort of compare the results produced by that tool. So this tool is not for every application. This tool works very well when you have tabular data, when you have some spreadsheet with some numbers and you want to find some relations between those numbers. This tool works really great. So it's not for all the applications, but it is for those cases where it works. It really works very well. So this is the collection of methods which are available in this tool. They range from simple clustering techniques to neural networks, and the interface is somewhat intuitive. You may want to take a tutorial before you use this tool for the first time. Once you use it for once, you kind of understand the logic and the flow, and you will be able to use it productively. But for the first time, there is something to learn there. We also have tensor boards. This is something that enables users to essentially monitor the execution of their machine learning jobs. So you can request, when you're, for example, running a model training, you can request some information to be stored during the training process in the format that tensor board can understand and then pick up at the runtime and visualize in the web browser for you. And so this way you can have an easy way to monitor the progress of your training jobs. Again, you have to specify what resources you need to run it. Typically, this tensor board is running on a separate node. It doesn't require much of resources. You just have to tell where to look for data, essentially. There is a format in the way that the data is collected, so you just need to point it to the location of the directory that needs to be monitored, and your training job will have to put data into the directory using the TensorBoard API. And then you can launch the interface, which, for example, might look like that, in this case, somebody is collecting a couple of characteristics about the training job, and these characteristics are updated each time there is a new piece of data added to the data set. So this is a very convenient way to have a very sort of easy interface. So you can imagine running a batch job where you submitted your job because you know computation is going to take 20 hours or so, and you don't want to sit and look at the numbers at the terminal to see if it's convergent or not. you can just redirect access to Tensor Board, and then you can occasionally just open the web browser and see if it's convergent. So this interface is there. And then one more interface that we have is VS Code server. So in the beginning, we enabled users to just run their VS Code clients on their computers and simply connect to one of the data nodes, which enabled the interface to the system, so that the remote connection from VS Code to the system. Now, because we are running Power 9 servers as in these interfaces, so these servers no longer, they basically never supported VS Code natively, so we had to run a separate service for this. So we actually added support for this VS Code server itself into our Open OnDemand interface. So all you have to do is just run it as any other interactive application here, and what you will get is full-blown code server, VS Code running in the web browser, and with the ability to, for example, download all kinds of extensions that are helpful in developing something, the ability to have access to files on the file system of the whole cluster, and with the ability to sort of edit code in your very sort of natural way, how you would otherwise edit it on your own computer. So so this service is available, and so we see a lot of users actually using it to write applications. And in fact, VS Code Server also enables you to run Jupyter notebooks as well. So you can open a Jupyter notebook directly here and be able to edit it and so on. There are some quirks in the way it's set up and it can be used. So for example, we run this server on a different x86 computer. So you do have access to the files and all that, but if you need to be able to actually have an active terminal through which you can run the code that you are writing on actual compute node, then you actually have to request a time on that compute node for interactive use. And so we have instructions to how to combine these things together so that you can have VS Code for editing files and then interactive shell on the compute node that would enable you to run those files somewhere as well. So this functionality is there. There is documentation on the wiki page which describes how exactly all this can be done. So are there any questions so far about any of this? I think at this point I would like to take a pause and see if there are any questions. Just turn on your microphone and speak up if you have a question. Okay, well, if there are no questions, let's have a very quick live demo with some of these tools. So we have a reservation made for this training so that we don't have to wait in queue for a very long time if we need to be able to just try something on the system. So the reservation name is HAL_training. So you're welcome to follow up with me to see how this can be done. So let me open shell terminal somewhere here. So for the very first time, when you only, so is there a question there? I don't see it. Can you speak it up? Or I guess I will need to.
Is it okay to?
Sorry.
Go ahead.
So essentially, when we're trying to use the URL, the link says that home directory not found. I believe we need to log, we need to SSH into the server, if I'm not wrong.
Yeah. So when you request an account and you receive an email saying that your account has been approved, the very first thing you need to do is to SSH into the login node. So I will type it in. So whole login 2.ncsa.lm. So when you SSH for the very first time into the login node, if your home directory doesn't exist, it will be created automatically. Unfortunately, it cannot be done through the Open OnDemand because Open OnDemand is set up in such a way that it assumes that the home directory already exists. So for the very first time, you need to find somewhere a terminal and SSH into it. And so, for example, I'm SSHing it from my Windows for Linux subsystem from my laptop. So I just type in my username at HAL-login2.illinois.edu and csi.illinois.edu. This prompts me to enter a password. So I will enter password. The password is not visible. And if the login is successful, if the password was recognized, then I'm going to get this question asking, so you have a dual factor authentication. If you have multiple of those, which one do you want to use? So I have only one, so I will use that one. And this sends me a message to my phone, so I can just have to confirm that this is me who requested this login. And that's it, I am on the system, right? So now I logged into the system. You know, at this point, you can forget about the user, this command line interface, because you can simply use the web-based interface. At this point, you can go ahead and just follow that link on the wiki page. And
could you please post this in the chat if that is okay?
Yeah, so I'm not logged into Zoom session right now, so I cannot post anything. But the you know, this is a pretty obvious link to remember. But I will show you how to very quickly find that link. But okay, so once you are here, you know, you can do your usual Linux stuff. So you can see what you have in your home directory. You can ask things like, what's happening on the system, SQ.
Excuse me, can you make your terminal a little bit bigger? It's kind of hard to see on Zoom.
Yeah, so what I had to do, perhaps maybe I can show it again. So I SSH into the system asks for the password. It asks for dual factor, so I tell which one to use for this. I confirm it on my phone. I am logged into the system. I can type in SQ to see what's in the queue. So this is sort of built into this learn command. And you can see there is a whole bunch of jobs running. This also tells on what node. So R means the job is running. Something here says something about the name of the job and who is the user who is running it. It's telling how long it's been running. It also tells on what resource, on which compute node, and so on. You will see that there will be these jobs which have this PD flag, which this says that these jobs are simply placed into the queue because there are no resources available to run them, or because the user already exhausted its fair share amount of resources. So we want everybody to have a fair chance to get his job running. So if somebody submits 1,000 jobs and somebody submits just one job, we want that person not to wait for until somebody else finishes whole 1,000 jobs. We want that person to have a chance to run his job much sooner. And so that priority indicates that all these jobs that have been submitted by these users, even if there are available resources, they are not executed because these users already exhausted their available amount of resources for a given period of time. And that fair share policy actually is described on our wiki page somewhere there, which sort of explains how exactly it's all computed. But yeah, and so some of these are running, others are waiting for, and so on. So SWQ gives you a visual view of this. I guess I will need to make it smaller so that it all fits here. Let me correct it. Let me adjust it real quick. Maybe not even that. So to be able to feed it all into one window, I reduced the font size. But basically now this is how this SWQ looks like. It basically shows exactly the same information as SQ before, however in this graphical form. And so it shows you which nodes are used and which GPUs are used. So you see there is a bunch of these nodes which are not in use. And that's because they are reserved for this class. So nobody else can use them because they are blocked from everybody else using. So you can only use them if you know the reservation key, and then you can make use of these nodes. So I will show you how to use that. So that's basically all you need to know in terms of how to check the status of jobs. And then, of course, if you want to run something, so for example, if you want to get something for interactive use, let me see if I have it in the history somewhere there. Yeah, so you can, if you submit just this, it looks like I don't see it well enough. Let me see. Yeah, so it looks like because there was an available resource somewhere that I was able to get a node for interactive use with 1 GPU. So I'm on some node with some number. You can ask, for example, what's available for me in terms of the number of GPUs. You can type in NVIDIA SMI, and this utility will tell you. So I'm not typing correctly. I apologize. I don't see. Oh, I'm typing.
Stream status in CPU node.
Oh, did I? Oh, yeah. So that's right. So I only requested a CPU node, so that's why I was able to get it very quickly. But basically, this tells me that there are no GPU devices attached for me because I never requested them. So if I want to, so suppose I use this node, I compute something on it, and eventually I don't need it, so I can exit. I can go and request a GPU node for my use. So I will need to specify GPU instead of N, it's X. So I will be requesting one compute node with 1 GPU for me. And so, so I'm placed into the queue because all the GPUs, if you remember this picture, there are plenty of nodes with available CPUs, but all the GPUs for those nodes which are not reserved, those are taken, those are used. So I'm placed into the queue, and you will have to wait a very, very long time to be able to actually get that node for the computation. So you can kill it. So Control-C will kill it. In fact, if you run now SQ and look somewhere for, perhaps I can just run SQ. You will somewhere see that I had a pending job, but I was not able to get it because the resource was not available. So this job was never satisfied. So let me see, I should have somewhere in my history example of running it with reservation. I wonder if that was, if I do have a reservation, I can provide that. I guess I don't have in my history anywhere, but so if I have a reservation, I can provide the reservation name, and then I will be able to get the queue. So you can see the documentation online about how to invoke the reservation. So let me now go to the web browser. Let me get to the web browser somewhere and see how we can use Open OnDemand instead. So we are going to go to wiki.ncsa. And to find the documentation, we will just search for word HAL. And so one of these pages will come up with the documentation. So this is the main page for HAL. If you need to request an account, there is a link somewhere here. Once you receive an account from us, you can sign up for the Slack group. And this is where you can ask questions to the support team. But you can also email. There is a direct email, so this will create a ticket in our ticketing system that one of our system administrators will receive if you have a question. But anyway, so yeah, and there is documentation for the new user in particular. There is this guide which kind of explains the whole process of how to apply for an account, how to get the username of the system, how to set up dual factor authentication, how to SSH into the system for the first time. So all this is described here. Anyway, one thing I didn't mention in my slides, there is also another web-based interface which enables you to see the status of the system. So it kind of shows similar information. It shows, for example, that some of these compute nodes are in use. This is their CPU status, and this is their GPU status. It also shows the list of all the nodes running, all the jobs running there, and also the utilization of how many users, how many jobs, how many are running, how many are in the queue, and so on. Also, I/O, for us who are developing something on the system to ensure that the system works well, we typically like to see how much I/O is happening there, so you can see what sort of memory bandwidth the system is sustaining, and so on, and also utilization of the storage system. But anyway, so this is secondary here. So here's a link to the Open OnDemand. So you can just follow this link. This brings you to this login page. So you type in your login. This brings you to the Duo page. And this actually sends you a Duo request automatically. So you just have to use your whatever the Duo authentication method you set up to approve accessing the system. And so it takes a bit of time to load the page, but now you have it. So this is the page that has access to all of those tools that I mentioned. And so I didn't talk about ML flow, but this tool is also there. In any case, so files gives you access to your file system, so you can see all your files here. You can upload and download files through the web interface. You can copy, move them through the web interface. You can create new files on new directories, and you can edit files as well. So if you have a file somewhere here, like this, there is a edit button, so you can get a web-based interface for editing it. So in principle, for any sort of very basic file manipulation work, this interface is sufficient. On the jobs side, you can see all the active jobs. So I ask it to show all of the jobs, but you can ask only to see the status of your job. So these are the two jobs which I tried, and it shows me their status. You can kind of see more details. In particular, what's the status? This one is pending, how much time I ask it, how much memory, and so on. So you can see all the details. You actually can see the same information for everybody's jobs. If you choose all, you can see that, for example, somebody's, so there are a lot of users who actually compute something on the CPU. This shows what queue they are in. Somebody is computing something on the GPU. You can pick, and it looks like there is more than one page. So we can see what's going on here, right? So this is somebody who is running Jupyter Lab as an interactive job, and these are the characteristics of this job. Now there is another panel here, the Jobs Composer, which enables you to set up the configuration for launching a job, and through this panel you can actually run it. So that Job Composer is there as well. So the cluster tab gives you access to HAL, and so this it attempts to place you on a node where you can have interactive access to the system. So again, it just gives you the same HAL interface as you would just SSH into the system. So it asks your password, asks your Duo factor, and so on. But this HAL lives completely within the web browser, so you don't need anything else. So you need HAL only once to initiate your home directory for the very first time. And after that, you can completely live within the context of the web browser. So, and then the most interesting part, of course, is this interactive applications. So Jupyter Notebook is perhaps the most frequently used one. So for example, if I want to run a Jupyter Notebook on the GPU partition, so I can choose this debug queue for 4 hours. I do have a reservation, so I can use the reservation name here. I want to request just one GPU and some number of CPUs. And if I click on this button, the scheduler is going to attempt to schedule my job to be executed on some compute node. So it takes a bit of time for this to refresh. And to show that our job is placed into the queue. And then, yeah, so it is showing that this job is currently starting because there were resources available for this reservation. So you can use the same reservation name to get resources yourself. And my session is starting, so I just need to wait for a little while just a few minutes to get the button which enables me to connect to Jupyter Notebook. And so here I am on this compute node, hall 01, where my Jupyter Notebook is running. And so I have the full, Jupyter Notebook interface. So I think I have some tutorials here to show you how, yeah, like this one. So for example, I have this intro notebook that I can open. And yeah, this is a complete notebook, so I can just execute it. So one important thing here is to choose the kernel. So when you start running, start a new notebook, and you need to decide which environment to use. So there are several of these kernels available. Typically you want to use the kernel which has the code that you need. And so looks like this is the latest version of the Open CAII environment. So I can open that notebook. That kernel, once this kernel is reloaded, then I will have all the tools such as NumPy and Matplotlib and all that available for me to run. And so I can start running the cells one by one. Somewhere here, there is a cell that generates some random data. So I will get random data set. There is a cell that does something else with this data. So if I run it, there is some computation happening and so on. And yeah, so this is a Jupyter Notebook. You can save it as usual, and you have the full functionality of this. You can go back. So the Jupyter Notebook is running there for the duration of the amount of time that you requested. You can kill it yourself if you don't need it anymore, and you can delete this job, or you can keep running it as long as you need it. The other tool which is very useful is VS Code server itself. Again, so you specify how many hours, what's the working directory that you want to connect to. There is only one version of it at the moment, so there is only one version of this. And you just click on the launch button, and this will enable you to launch this server, VS Code server, through which you can edit files and write your programs. Again, this takes a little bit of time because this is the job that is submitted into the Slurm scheduler, and the Slurm scheduler needs to find the place for it to be executed based on fair share, on the available resources, on the amount of resources that you requested, and so on. So if you look at this, you'll see that here is my notebook running here, and then there is VS Code. So eventually this button appears here, which indicates that now I can connect to the VS Code server. And this VS Code server, this is a full-blown server where I can go and open files for editing and so on. So for example, this is the code for EC48, which I teach this semester, and so I can take a look at the CUDA code, and so it has all the benefits of using VS Code with the file system that sits on the whole server. And actually, you can switch between notebook and VS Code and any other tool that you want to run within your environment. Now, once you're done with this and you should no longer need any of that, you can just delete these jobs, and these jobs will go away. And I can delete this as well. And these resources will be returned back to the pool of resources so other users can use it. And similarly, you can launch these other tools as well. All right, so any questions about this?
I have a question, please.
Sure.
So I was trying to submit a job as you were doing, but I'm getting an error when I click launch. So I'm getting an error that says that failed to submit session, and then it says invalid account or account partition combination specified.
Yeah, so there is something here that you did not specify correctly. So which one did you try to do? Did you try the Jupyter Notebook, or what did you try?
I tried both, actually.
Well, what did you provide for the reservation, for example? Did you have anything for reservation?
Yeah, so it's HAL underscore training, right?
Yeah.
And
So
then
try something like this. Try something like this and see if it works.
so it's 1 GPU, 4 CPUs, and then a debugging partition.
Mm-hmm. And HAL training so that you do have access to the pool of reserved resources.
Yeah, someone in the chat is having the same issue as well. So it's loading, but let's see.
Well, so it takes a little bit of time. You notice that it took time for me as well to learn.
Yeah, so I'm getting the same issue or error again.
Yeah, the same problem is also for me.
I see. Yeah, so I think actually, all right. So please post this as an email as either into our ticketing system or on Slack channel. I think so this is a bug that we know. If you first tried to use Open OnDemand before SSHing into the system, then something gets messed up with the way your home directory is created, and that interferes with the ability to launch these jobs here. So system administrator will have to fix something in your home directory, run some initialization script that didn't run properly. So post this question in the technical support channel, and the sysadmin will get to you and will fix this. That's just a side effect of you not trying to SSH into the system first. Okay, any other questions or any other issues? So I think, the thing that I wanted also to point out, this documentation. There is quite a bit of documentation. It shows there is more than 20 pages here. So there is a page how to use VS Code with GPUs on HAL. There is a page which talks about how to use multiple GPUs for distributed deep learning. There is something about getting started with HAL OnDemand. It sort of has the description and the step-by-step tutorials about how to work with different tools here. So there is a page which also describes what sort of software we have there. So there is a job management with Slurm. So this one has a detailed documentation about how to use these different commands, how to write different scripts, and there are plenty of examples, and also this table with some information about the different partitions and different implications for amount of memory available for you and so on. So we have this hard-coded somewhere there. So there is detailed documentation about how to use that. There is also documentation about modules somewhere, module management, and in fact, you can see what modules are installed there. So we try to maintain current list of installed modules and provide the description of how to use this. And then there is a table somewhere here with OpenCAII, right? So this is a popular tool. So this basically provides some documentation about how to load a particular module and then how you can use this. But there is actually another page somewhere here. Let me see. Oh yeah, how to configure Python environment. This is actually something that is very frequently asked. So you typically, we never can provide all the tools that you need. Very frequently, you will need to install some of the tools yourself. And so typical way of doing this is to start with one of the environments which has most of what you need, and then clone it. So for example, this example shows how to clone OpenCAII version 1.5, 1.1, and then you can install in your local environment all the missing tools. And this way you can get all the packages which you need to get started with. And so there is the documentation how to sort of come up with sort of environment, custom environment, which is needed with your for your application. Okay. So any questions? Any other questions? So you are welcome to, we have a bit of time left, and this reservation will be active for another hour or so. So you're welcome to try to play around with these tools using this as a reservation. So you can, try to get feeling about how to use these tools. But I think that actually concludes our training session today. So let me know if you have any questions. I can stay here for a little longer.
May I ask about how can we get the reservation code when we are actually using HAL for maybe research purpose?
Yeah. So you typically will post something into the technical support channel on the Slurm. I'm sorry, on Slack, or you will submit a ticket into our ticketing system. You can try to email me directly, or you can try to email system administrator, who is Jan Zan. I don't think I see him here, but a desirable way would be to post it through through one of those more standard channels. Yeah, and so on this page, on this whole page, you will see there is a link to request access to this group on Slack, where you can, all the users of the system are there. You can talk to them, or you can talk to the support team if you need help. All right. Any other questions? Yeah. So I would urge everybody to sign up for this Slack channel so that you can have access to more or less, quick enough response from us. One of the things, there is a disclaimer somewhere here about the use of the system. I guess it's not here anymore, but the disclaimer is that we provide the system on the best effort. So this system is not guaranteed to be online all the time, and we provide access to the system only as good as we can. So typically we fix problems within 24 hours, usually much faster than that, but we do not guarantee immediate response. So if you do not get the response within a few hours at 12 at night, then we do not guarantee that response will be provided that fast. But eventually we will get to your request, and eventually we will fix it.
I have a question regarding uploading files on the system. So we saw how to upload like Python files or codes using the website, but regarding the datasets, for example, if I have MNIST or ImageNet or other datasets, do I upload these as well for training, or?
Yeah, actually, talking about those datasets, let me see if I still have my terminal open somewhere. So some of these data sets are already available on the system. So if you go to CD, share it, somewhere here. So this is a shared space where different projects have space somewhere there. These directories belong to different groups, and typically you only have access to what you have access to, if you're a member of that group. But there are shared data sets. So there is ImageNet, which is available for everybody to use. Something like MNIST is not a particularly large data set, so you can download it for your own use. But ImageNet, that data set is already available. If that data set has a direct link, so first of all, MNIST probably will be downloaded through the data loader that is built into one of the example applications. So you will kind of get it automatically when you try to run something for the first time that uses MNIST. Right, those examples that use MNIST, they have that code built in. So some of those data sets can be downloaded that way. That typically is true for small data sets. For ImageNet, that is not the case. So if the data set has a direct URL where you can just point to that URL and get the actual file, you can use wget. So from that web space, from that web page. So wget will fetch that file for you. So if you can find the exact path to a data file, you can download it this way. And now, if you have data on your own laptop, The simplest thing to do would be just, and if it's just some number of gigabytes, even tens of gigabytes, that's actually not that much. So what you can do, you can just SCP that data from your laptop, from your own computer. Use SCP command. So you will need to be on your own. So let me exit. Yeah, so I'm disconnected. So I'm on my own laptop. I have some files in my home directory. So I can type in SCP, my file to what location? Volodymyr2.ncsa.edu at the location home Kinder. And so if I hit enter, my file will be copied over SCP protocol to that location on the whole file system. So that's another way. So if this is just some small number of gigabytes, that's easy enough to do. Now, if you have a large number of files or a large collection of files, it's always a better idea to try to compress them into one archive file, transfer one file, and then uncompress it there. It will be faster. And I'm sure there should be documentation somewhere here how to transfer data using how to use endpoint for the Globus transfer as well. So we do have the documentation somewhere, so you should be able to follow that. Yeah, I don't see it from here, but we do have it somewhere, so you will be, or you can ask us and we will provide you a link to that. Yeah, data movement on HAL. So this is how to do it with different tools. Yeah, so there is a description how to use different tools for this.
Okay, I see. Thank you.
I think it all depends on how much data you have. If this is not that much data, then that's an easy procedure. If there is a lot of data, then you probably will need to use. And if the data is located on somebody else's supercomputer somewhere else that also has Globus endpoint installed, then that would be the best way. Okay, so I think in this case we are done for today, and thank you very much for coming to this tutorial. This video is recorded and eventually it will be posted online somewhere there, so you can always come back and rewatch it. And the PowerPoint slides also will be posted online. The typical place where we post this is ai.ncsa.edu. If you go to this website and you look at the whole training, you will see that this presentation and video links appearing here. Right now, we still have training sessions from the spring semester, but we will be replacing them with this newly recorded training sessions. And the previously recorded training sessions will be available somewhere here in the subfolders. So you can always look at this training materials later on. Okay, thank you very much. We are done.